Hello, this is our optional project video for our physics class. My name is Edras Ortiz Coronado. I am a first year here at WashU and majoring in mechanical engineering.
Hello, I'm Brendan Maldonado. I'm also a first year here, majoring in mechanical engineering. Today, we're going to be testing different rubber bands and testing out different orders of them to see which is the most effective way of launching a projectile using this launcher here.
Hello, I'll be presenting you our mechanism that we created using the resources here provided at WashU. For example, we use the makerspace in Jubal Hall, and we also use the Givens Wood and Metal Workshop in Givens Hall. Here is our beautiful mechanism made out of wood, holding a 45-degree angle, having two support beams on each side. Here can be seen visible. The front one helps it prevent from falling down, tipping over like this way. And this one is for additional support to help us keep that 45-degree angle. This is our launcher track where our object will be shooting from. And these two rods will help us put on the rubber band so we can shoot it. This is fastened into the launch track. And this is our mounting block where we're gonna input the different type of rubber bands at either series, which means over each other, or parallel, where it's each rubber band is like a ladder of some sort. Here we have holes so we can change the different rubber bands, the number of rubber bands, and any additional changes we have to do. Here we insert the rubber bands, and then we use this little notch to just slide it in and hold it in place. Once we have the rubber bands needed and how we want them set up, depending on what job we're on, we can just put it in here. Let me get this. So here, preferably with two hands, using one because we can just put it right there and set it up however we want it, if it's parallel or in series. In this case, the parallel. So here you see how they don't overlap, but they're pretty close together. Same thing, well, almost same thing here. Yep, perfect. And then this is what we have for our mechanism. Pull back here and then let go and it shoots. You will be seeing that in our future tests. This is our projectile that we're going to be launching. It consists as a cardboard cylinder filled with paper towels and a metal rod in here that's not as visible, covered with tape, and it weighs 0.6 pounds, which is about 0.27 kilograms. This is the projectile we're going to be launching for each experiment. The constants of this experiment is the temperature of the room, which is room temperature, which is 70 degrees. Also, the amount of extension that we're going to be putting on the rubber bands, which is at the edge of this track, and letting it go evenly so it launches to the distance it wants to do. Now going into our independent variables, it is the number of rubber bands. How are they placed? For example, if they are in series or parallel. Series is when they're overlapping each other. Parallel when they're not overlapping each other, but they are pretty close. And the number of rubber bands. So those are the two independent variables. And then the dependent variable is the distance of our projectile from each test that we do. So we'll be, of course, testing the number of rubber bands and how they're formatted or set up. In this case, whether if it's parallel or in a series. The way we recorded our distance each time was putting moisturizer on the tip of the projectile and it hitting the carping, leaving a mark, and that's how we measured the distance from the edge of our launcher to where it would land.
Here are the three different kinds of rubber bands that we have used for this experiment that vary in length and in cross-sectional area. We only bought one brand because we understand that if there was a chance that we bought a different brand of rubber bands along with these, there was a chance that they were manufactured differently and they would have different ranges and would react differently when we were to test out their spring constants and how far they can stretch. Rubber bands' spring constants are affected by three things. pressure, temperature, and cross-sectional area. To put it simply, the greater the cross-sectional area is, the harder it is to stretch. For example, these would be the most difficult to stretch, whereas these are the easiest, shown by how it was easier to stretch it to 22 inches, whereas this one is only into 17 inches, showing that has a higher potential for higher spring constants. Rubber bands are not ideal like springs usually are. There is a chance that they can become permanently deformed and the Hooke's law will no longer apply to them. And they don't have a single spring constant like other springs do. Instead, they have like a large range of spring constants that can range from low to high that will vary based on the cross-sectional area of the rubber band. Here is the data we've collected from all the experiments we performed. We categorized these experiments using three things. 1. The quantity of rubber bands used. 2. The size of the rubber bands. And 3. The order they were in, whether it was in series or in parallel. However, there's an exception to this with these three, where there was only 2 rubber bands used for each size. However, they could not be categorized as either series or in parallel because these 2 rubber bands were tied separately to separate wrongs. So they were only used to compare the effect the cross-sectional area has on the distance the projectile travels. 3 trials was performed for each of these, and they were averaged out, and the standard deviation of them was used using this formula. The times for each one was also taken into account. The average was taken, and the standard deviation was also taken. Here is a log/pro graph of the first data table shown. We only put into account the averages of the distance traveled for each experiment. The first 3 here is the 3 that didn't have a specific order. However, they show that the larger the cross-sectional area is, the more distance it travels. Since this is the smallest, this is medium, and this is large. Then they follow a pattern of 4, 6, 4, 6, 4, 6 in the quantity of rubber bands. And then the sizes go from small, medium, and large. There's a clear trend here where the dark red points, which demonstrate the parallels order, is always greater than the series, which is the light red points. Even though if there's a minuscule magnitudes in difference, we could clearly see that it would always become greater and not less than the series. The sizes of each rubber band was generalized as just small, medium, and large rather than an actual number for cross-sectional area because our focus in this experiment was not to take into account the specific area of each rubber band, but rather acknowledge the fact that the cross-sectional area does take an effect on the distance traveled by the object. The larger the rubber band, the farther it travels. Our primary focus was the order of the rubber bands, which we see here. The parallel was the greatest of them all. And then, for the spring constant, the rubber bands does not have a singular spring constant. Instead, they have a range. So, to avoid that problem, we would always stretch each and every single experiment to the same exact point. So then they would reach to a certain specific spring constant rather than having several at different points of the launch. Finally here, we have a relationship between the time to land and the type of rubber band. Although there is not a consistent trend along this graph is just meant to illustrate the time it took for the projectile to land at the distance traveled. There happens to be a bunch of discrepancies along this graph, which could be chalked to two reasons. One of them is a systematic error. When taking the video of the projectile being launched, there happened to be an error when calculating the exact time that it landed. Therefore, two is that there are external factors that plays into effect of how much time the projectile remains in the air. For example, whenever launching the projectile, it was slightly leered to the left or to the right, causing it to be launched into another direction rather than our intended straightforward direction. So therefore, it would cause the projectile to be in the air for slightly lower or higher amounts of time than intended. The main conclusion we could come with is that the parallel order of the rubber bands is the most effective way of launching an object to the farthest distance possible. Regardless of the size and quantity, we could see that using it in parallel will always produce a greater distance, whether there are small quantity or smaller size.